One thing that's nice about substitution reactions that's not nice about elimination reactions is when you're doing a substitution, pretty often the new thing will end up bound right where the leaving group was. Unfortunately, that isn't necessarily the case for E2. In fact, you almost always end up making two different double bonds, or at least you need to contemplate making two different double bonds. Now, of course, when you're doing substitution reactions, you have to pay attention to carbocation rearrangements, and that too exists in eliminations. But in E2 eliminations, you're almost always going to have a choice as to where the new group will end up, the new double bond will end up. And that's because if the leaving group is at the alpha carbon, then frequently there are hydrogens to potentially be abstracted at both beta carbons. And so the hydrogens that could be abstracted for the beta elimination are present on both carbons. And therefore, when you have the sodium hydroxide coming in to potentially do a deprotonation, it's possible that you would abstract one of these three hydrogens or potentially that one, because there are four hydrogens at the beta position that could potentially be abstracted. Of course, you need to think about anti-periplanar arrangements and so on, but in this case, we can kind of rotate around freely, so any of those hydrogens can access the anti-periplanar location such that then they can even be eliminated. My advice mechanistically is always to consider sodium as a sodium plus unless you know that it's sodium metal, and therefore you really should think of this as sodium plus and OH minus floating around. So OH minus is going to be the thing you use when you draw out this mechanism, and then we really have two mechanistic pathways to pay attention to. One is this oxygen can come by and pull off one of the three hydrogens at this beta position, and what that will do is cause those electrons to flow that way. The end result being a double bond that is terminal and monosubstituted. And so if you're paying attention to your alkene stability, you recognize this as a relatively unstable alkene. But there's another potential mechanistic arrow as well, and that is that this red path could happen, and instead this oxygen could come and abstract this hydrogen, which would cause this to collapse down and the bromine to leave, which of course I admitted to draw the first time through. Following the red path, when you do this abstraction, what you end up with is an internal double bond, and it's actually going to be a tri-substituted internal double bond. So if you're looking at these two choices, you should recognize the internal and tri-substituted double bond as substantially lower in energy than the terminal one. A Russian guy at the turn of the century who was doing a lot of elimination type reactions and realized that this sort of leading to the more substituted product is the thing that would happen, especially if you had the chance for a relatively weaker, relatively milder base to do the abstraction. That this was the preferred thermodynamic outcome. This is the more stable product. And so if you have a relatively weaker, relatively milder base doing the abstraction, you're going to make more of this product just because it's lower in energy. Even though there's three chances to abstract one of those hydrogens, it's harder to do that, and so you make less of it. And one of the key features to recognize here is that the pKa for the hydroxide is about 16, which makes it both a strong base in some senses and relatively mild as most organic bases go. By contrast, LDA is a much, much stronger base, lithium diisopropyl amide. LDA, if you simply have it stored away in your memory banks as 42, that's great, but if you don't remember LDA specifically and you're just thinking about a nitrogen with a minus on it, then I'd want you to remember that from the short list as being about 35. Regardless of which way you're thinking, though, it's clear that there's at least a 10 to the 20th difference between these two, and therefore LDA is a vastly stronger base than hydroxide. Also, it's huge. Hydroxide is tiny, and this is absolutely massive, and what that means is that there's really not much chance of the LDA coming by and trying to abstract this particular hydrogen. Though it could happen, it's just exceptionally unlikely, and so you're not going to be making hardly any of the internal products. It's possible, but again, the barrier for accessing those products is extremely high. Instead, what's vastly more likely to happen is that the LDA will abstract one of these much more accessible hydrogens and pull them off on the way to kicking out the bromine. In other words, the LDA is specifically going to form the kinetic product. It's easier to access these. It's a higher energy product, but it's much quicker. There are three hydrogens, they're much more available. This is going to come by and abstract one of those, and it's essentially not going to extract the internal one to form the Zaitsev product ever. This quicker product is known as the Hofmann product, and basically the stronger your base, the more biased you are toward abstracting the Hofmann product. The milder your base, the more likely you are to be able to abstract the Zaitsev product. And that's because this is a lower energy product in the end. And so if your base is relatively selective, it's probably going to bounce off these a couple of times and not really react with them because it leads to a relatively higher energy product. Whereas if you can get at that little one, then you can get on down to the desired thing. And it's generally the true that part of the reason why that's happening is because this is a smaller and weaker base. One of the reasons why you can't access the internal Zaitsev products with this relatively large large base is because that makes the barrier for abstracting that higher. It raises the energy level of that. But it's also the case that LDA, being so strong, is just less selective. It's going to rip off the first hydrogen it encounters, and it's more likely to encounter one of these than it is one of those. So it's simply going to access and remove the accessible hydrogens first, which leads to the kinetic product, which we term the Hofmann product. One of the key features about the Pelkey E2 handout is its description of the regioselectivity of the reaction. And specifically, he says that E2 regioselectivity is under kinetic control. Thus, the major product is formed via the most stable transition state. And what he's talking about is these reaction coordinate diagrams down here. And basically what he's saying is you're always going to go via the pathway that has the lower hump, that the height of this transition state is the thing that determines which product is formed. And so even though the Zaitsev product is lower in energy in both cases, if the hump you have to get through is low, you'll go there. But if the hump you have to get through is high, then you can't access that. And again, what matters is the height of the hump, not the height of the two products involved. So the small base that we're using, like say sodium hydroxide, then has a relatively low hump for the Zaitsev product because you're going from here down to a lower energy thing, and therefore this is a relatively low energy pathway. And by contrast, going to the higher energy product leads to a higher energy hump to get there as well. And so really the height of the transition states is determined largely by the energy difference of the two products. Now what happens when we use a much larger base, like say potassium T-butoxide or LDA, lithium disopropylamide, is that the transition state number 2 really doesn't change for either one. You'll notice that it starts at the same energy in both reaction coordinate diagrams, and it ends at the same energy in both reaction coordinate diagrams, and the height of the transition state is the same in both reaction coordinate diagrams. Accessing these hydrogens that are out here is essentially the same, no matter how big your base is. However, if you're trying to access the hydrogen that requires a smaller base to get in there, then the height of the transition state absolutely depends on the size of the base. The smaller your base, the lower the height of that transition state. Whereas with a relatively large base, if you're still trying to get in there in transition state 1, what happens is it ends up being quite a bit more challenging, and that's because your base will simply be bumping into the other stuff that's present. So the message here is simple. If you have a small base, you're going to form the Zaitsev products preferentially because those are the lowest energy products. However, with a larger base, it's going to be preferential for the Hofmann product, and that's because the Hofmann product really doesn't depend on the size of the base very much, whereas the Zaitsev product absolutely does. And with a small base, you have a low hump to go over, and then therefore it goes to Zaitsev. And with a large base, you have a high hump to get over, and therefore you can't get there, even though it would be lower energy in the end.